Uy, okay na ba?
Ako na ba?
I'll be discussing the definitions and terms.
I'm Greg Kenneth Bredicina and I'm going to discuss the real-life examples.
Hi, my name is Daria Mario and I'm here to give and to discuss some examples for us to understand the topics that my groupmates and I will be discussing.
So what are you waiting for?
Let's go!
First off, we will tackle about thermal expansion. Thermal expansion is the tendency of matter to change its length, area, and volume in response to a change in temperature. Generally, dimensions increases as temperature increases. There are three different types of thermal expansion. First is linear expansion, area expansion, and volume expansion. The linear expansion is applicable in case of rods, wires, or cables. The general equation in linear expansion is change in length is equal to alpha multiplied by initial length multiplied by the change in temperature. Next is the area expansion. It is applicable in case of metal plate, change in area. The general equation of area expansion is change in area is equal to gamma multiplied by initial area multiplied by the change in temperature. Lastly is the volume expansion. In this case, it is applicable for metal block. The general equation of volume expansion is change in volume is equal to beta multiplied by initial volume then multiplied by the change in temperature.
Hi, so today I'm going to show you a real-life example of a thermal expansion using this glass jar steam. The jar's lid is really tight. How can I open this?
Now, we are going to try pour some cold water on the lid to see what will happen. After the cold water approach, the jar's lid is still tight. Based on what I learned from the previous lesson, thermal expansion is a tendency of matter to change its shape, area, and volume in response to a change in temperature. What if I try to increase the lid's temperature? Its area can also be increased, and it can cause an expansion.
So, the experiment is a success. The hot water caused an expansion to the jar's lid, and the cold water caused a contraction.
So let's try to solve this problem that tackles about thermal expansion. At 20 degrees Celsius, the length of a sheet of steel is 50 centimeter and the width is 30 centimeter. If the coefficient of linear expansion for steel is 1 times 10 raised to negative 5 degrees Celsius raised to negative 1, determine the change in area and the final area at 60 degrees Celsius. By analyzing this problem, we know that the initial temperature is equals to 20 degrees Celsius. The final temperature is equals to 60 degrees Celsius. And if we subtract the final temperature to the initial temperature, 40 degrees Celsius would be our change in temperature. In getting the area of a rectangle, we multiply its length and width. 50 cm times 30 cm is equals to 1,500 cm squared, which would be our initial area. If the coefficient of linear expansion for steel is equals to 1 times 10 raised to negative 5 degrees Celsius raised to negative 1, since we are getting the change in area, we need to convert our alpha to gamma. 2 times 1 times 10 raised to negative 5 degrees Celsius raised to negative 1. Our coefficient of area expansion for steel is equals to 2 times 10 raised to negative 5 degrees Celsius raised to negative 1. We are required to solve the change in area and the final area at the temperature of 60 degrees Celsius. By using the equation, change in area is equals to gamma times initial area times change in temperature. 2 times 10 raised to negative 5 degrees Celsius raised to negative 1 times 1,500 centimeters squared times 40 degrees Celsius. We were able to get 1.2 centimeters squared as our change in area. And by getting the final area, we just have to add the initial area to the change in area. That is why we were able to get 1,501.2 centimeters squared as our final area.
The next course outcome is about wave. Let us define first what is wave. The wave carries energy from one place to another. There are two different types of waves. First is the mechanical waves. These are waves that are produced in matter such as solid, liquid, and gas. The second type is electromagnetic waves. These are the waves that produce in electric and magnetic fields and can propagate even in vacuum or empty space. Under mechanical waves, there are two types, the transverse waves and the longitudinal waves. On this discussion, we will be focusing on transverse waves. These are the waves occur when the particles of medium vibrate perpendicularly to the direction of the propagation.
Hello everyone, so it's me again. Now, I'm going to discuss to you the real-life application of a transverse wave, a mechanical wave. As what you saw, I can create a wave-like figure by just moving my hand vertically up and down. In transverse wave, the particles are displaced perpendicular to the direction where the wave travels. That is a real-life example for a transverse wave.
The second example, we try to solve a transverse wave. Two points, A and B, are on the rope and 90 cm apart from one another. On the rope propagates the transverse waves. That point A is at the top of the wave, point B is the bottom of the wave, and between them, there are two crests and two troughs. If the wave period is 0.3 seconds, then what would be the wave propagation? Given that the distance between A and B is equals to 90 cm, the period of wave is equals to 0.3 seconds, and the frequency of wave is equals to 1 all over 0.3 seconds. And based on the figure, we concluded that there are 2.5 wavelengths. And to find the distance of the wavelength, we divide the distance between A and B to 2.5. And therefore, 36 cm is the distance of the wavelength. To find the speed of the wave, we will use the general wave equation. Velocity of propagation is equals to frequency multiplied by the wavelength. 1 all over 0.3 seconds times 36 cm is equals to 120 cm per second. Our velocity of propagation is equals to 120 cm per second.
The last course outcome is about electrostatics. Electrostatics is a science which deals with the study of electric charges and charge systems at rest. We will be focusing about electric charges, which defines as the quantity of electricity a body possesses. It is the amount by which the negative particles in a body exceed or less than the positive particles in it.
Hi! So today, I'm going to show you a real-life example for easily understand the electric charge. The best example for you to easily see the idea about the charges is this magnet. Like the electric charges, magnet has its own repulsive property that best describes the topic that we are discussing.
This last example is a problem that tackles about electrostatic. Three charges lie along the axis as Q1 is equals to 6 microcoulombs, Q2 is equals to -2 microcoulombs. Determine the magnitude and direction of the net force on Q3, which is 1.5 microcoulombs. There are two Coulombs forces acting on Q3. F1 is the force acting on Q3 due to Q1. F2 is the force acting on Q3 due to Q2. We can find the net force by vectorially adding these two forces. First, we need to draw the free body diagram for Q3. We will draw two forces acting on this charged particle. F1 is directed to the right because Q1 and Q3 repel each other. And F2 is also directed to the right because Q3 and Q2 attract each other. We will determine the magnitude of each force considering the absolute value of the charges. Then, we will add vectorially the two forces considering their direction. Using the formula in Coulomb's law, F is equals to K times Q1 times Q2 all over R squared. K is also known as the Coulomb's law constant. F1 is our force 1 and F2 is our force 2. The equation for F1 is F1 is equals to K times Q1 times Q3 all over R sub 1 raised to 2. 9 times 10 raised to 9 Newton meter squared per squared coulomb multiplied by 6 times 10 raised to -6 coulomb times 1.5 times 10 raised to -6 coulombs divided by 1 meter squared. F1 is equals to 0.081 Newton. The equation we use in solving F2 is F2 is equals to K times Q2 times Q3 all over R sub 2 raised to 2. 9 times 10 raised to 9 Newton meter squared per squared coulomb multiplied by 2 times 10 raised to -6 coulomb times 1.5 times 10 raised to -6 coulomb divided by 2 meters squared. F2 is equals to 0.007 Newton. And in finding the net force, we just have to add F1 to F2. Our net force is equals to 0.088 Newton.
Rolling.
Thank you for watching!